Hello everybody. We're going to go over the fundamental theorem of calculus today. There's two versions of this theorem, and we're going to go over version 1 today. We're going to do 4 examples together, and then we'll cut you loose on some practice and working on your quiz. I'm at a meeting, and hopefully we'll be back here by the end of the period. But let's get started. The fundamental theorem says that if a function f is continuous on a closed interval from a to b, and capital F, big F, is an antiderivative of little f on the interval from a to b, then the integral of f of x with respect to x is going to be computed by taking the antiderivative big F evaluated at b minus big F evaluated at a. Let's see what that means with some examples. The first example we're going to do is from your note sheet, problem number 2. You see the integrand is 3x squared minus 2x minus 1. So we're going to start by integrating this guy. The integral of 3x squared is going to be 3x cubed over 3. And you see that the 3's cancel, so you just have x cubed. The integral of 2x is going to be 2x squared over 2. And the 2's eliminate each other, and you're just left with x squared. Let me clean this up a little. The integral of minus 1 is just minus x. And now we usually put a plus c. And when we have a definite integral, we're not going to put the plus c. I'll explain why a little bit later. So now what we need to do is take this whole expression and evaluate it twice. Once at x equals negative 1, the lower limit of integration, and once at x equals positive 3, the upper limit of integration. So what we've just found is that big F of x is, in this example, x cubed minus x squared minus x. If we were to differentiate big F, we'd get the integrand, little f. So now what we're going to do is we're going to set up two quantities and subtract, like so. So the very first thing we do is we take the upper limit of integration and substitute 3 in for x. So instead of x cubed minus x squared minus x, we're going to get 3 cubed minus 3 squared minus 3. Then we're going to subtract the quantity that results from taking the lower limit of integration, negative 1, and substituting this in for x, which is negative 1 cubed minus negative 1 squared minus negative 1. And like with many things that we do, the first time we go through an example or a few examples, we're going to do a lot of writing. And as you get practice, as you get familiarity, as you gain familiarity, that is, you probably write less and work a little more quickly, more fluently. So now let's just simplify. Let's evaluate, see what we get. This is going to be 27 minus 9 minus 3 minus negative 1 minus 1 plus 1. Let's see, 18 minus 3 is 15. Negative 2 plus 1 is negative 1. 16 is the value of this antiderivative. So this tells us a couple things. Number one, if we were to graph y equals 3x squared minus 2x minus 1 on a grid and find the exact area between this curve and the x-axis on the interval from negative 1 to 3, that area would be 16. No approximations, this is exact. And what does that tell you? Well, if the integrand is representing a velocity function, we find that the displacement on a given interval is 16, which means the object ended 16 units from where it started. So depending on the context of a problem, this integral can tell you different things. Our first example is down. Let's move on to our next example. Example number 2 is going to be problem number 6 from our note sheet. Well, let's get started. You notice the integrand here is a little more complicated, so what we need to understand is that we're going to have to simplify. We're going to have to do some algebra. X divided by x to the 1/3 power minus 2 divided by x to the 1/3 power. That's how we're going to think of simplifying this. Well, x over x to the 1/3 power is x to the 2/3. Remember, there's a 1 in the corner here in the exponent. We subtract the exponents when dividing terms with the same base. And if you rewrite the second term, you're going to get minus 2x to the negative 1/3 power. So now we can continue. we can say that the integral from 1 to 8 of the quantity x minus 2, it's a bad looking 2, let me clean it up, over the cubed root of x is going to be this. Let's integrate this guy now. So let's add 1 to the exponent. 2/3 plus 1 is 5/3, and we'll divide by the new exponent. Dividing by 5/3 is the same thing as multiplying by 3/5. Now let's go minus 2 times x to the negative 1/3 plus 1 is positive 2/3. And now we'll divide by 2/3, which is the same thing as multiplying by 3/2. We're going to evaluate this expression at x equals 1 and x equals 8 and subtract. This looks nasty, but I think it's going to work out well. What a great opportunity we have here to review some algebra. So let's see. The first quantity minus the second quantity. We're using the fundamental theorem of calculus to evaluate this integral. The very first value we put into our antiderivative is 8, x equals 8. So it's going to be 3/5 times 8 to the 5/3 power. No calculator necessary. And you see here, when we subtract 2 times 3/2, the 2's are going to cancel. So we're really going to just be subtracting 3 times x to the 2/3. In this case, 8 to the 2/3 power. Then the next thing we'll do is go to the other quantity and substitute 1 in for x. This is going to be 3/5 times 1 to the 5/3 minus 3 times 1 to the 2/3 power. No calculators required. Okay. Let's first review what some of this fraction exponent notation means. When we have 8 to the 5/3 power, that means the cubed root of 8 to the 5th power. So the cubed root of 8 is 2, and 2 to the 5th power is 32. So we didn't need a calculator. We can do this problem with pencil and paper. So let's clean this up now. The first quantity is going to be 3/5 times 32 minus 3 times, again, let's figure this one out on the side, our scratch work. 8 to the 2/3 power means the cubed root of 8 squared. Cubed root of 8 is 2, so 2 squared is 4. It's going to be 3 times 4. And the next part is nice and easy when you have a 1. 3/5 times 1 to the 5/3, just 3/5, minus 3 times 1 to the 2/3, it's just 3. Okay? And again, we can clean this up now. We don't really need a calculator. We can use a calculator. Let's see what we get. So let's see, we would end up with 7.2 plus 2.4, which is 9.6. Now again, we might have made a careless error running through this problem quickly and mentally, but I think it's right. We're practicing these skills now, integrating functions using the fundamental theorem to evaluate a definite integral. We have 2 more examples to go. Let's go to the next one, which will involve some trig. Please feel free to pause the video anytime if it'll help you let things sink in and make sense of what we're doing. Okay, example number 3 is going to be problem number 7 from our note sheet. Let's see what we have here. If you integrate 2 with respect to x, we get 2x. And if we integrate sine, we're going to get minus cosine of x. We're going to evaluate this one from x equals 0 to x equals pi. All right. Well, I think you know what's coming next. We have one quantity minus another quantity, and we'll substitute some values in. Let's first put pi in place of x. So 2 times pi minus the cosine of pi. You write that neater. And then we'll come around and the next time substitute 0 in for x. 2 times 0 minus the cosine of 0. And let's simplify. 2 pi minus, let's see here, the cosine of pi. Pi is over here. Cosine is the x-coordinate, so that's minus -1 minus 2 times 0, which is 0, minus the cosine of 0. Well, 0 degrees, 0 radians is over here. Cosine is the x value. X is 1 in this case. So we're going to get 2 pi plus 1 minus -1, 2 pi plus 2. If you want to get a decimal approximation, you can type that into your calculator. Otherwise, here's the exact answer. Again, the meaning of these values will depend on the context of a problem. Right now, we're just working on scales. There are no units. There's nothing for us to really tie this to. Let's go to our fourth and final example for today. We're talking about integrating the absolute value of 4 minus 2x. Whenever you see absolute value, whether we're differentiating or integrating, it's really a good idea just to sketch a graph. So we're going to do two graphs here. I'll show you how to sketch an absolute value function graph if you're not sure. All right, and let's see, we're going to go from 0 to 5. 1, 2, 3, 4, 5. One, two, 3, 4, 5, 6, 7. All right, so let's go to work. In green, we're just going to graph y equals 4 minus 2x. No absolute value yet. We're just going to graph y equals 4 minus 2x, because this is something we can all graph. We can tell this is going to be a line whose, oops, hold on a second. Let me change the scale here and go like this. All right. So now the y-intercept is going to be 0, 4. Up here, the slope is -2, which means you come down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, down 2 and over 1. We get a graph like this. It's supposed to be a straight line. Use your imagination. This is the graph of y equals 4 minus 2x. Okay. Now, they didn't ask us for just 4 minus 2x. They asked us for the absolute value. So now I'll show you how to use this graph to get the absolute value. We're going to graph now in red y equals the absolute value of 4 minus 2x. So think of the y values here. In the very first part of this graph, the y values are positive. And when you take the absolute value of a positive, your answer remains positive. Nothing changes. So the beginning of our graph remains exactly the same as the original graph. Okay, next, we're going to look at what happens when y equals 0. Since the absolute value of 0 is 0, this point will remain unchanged. Now, this is the money step. Since these y values are negative, when you take the absolute value of a negative, you get a positive. So these y values are going to be flipped, become positive y values, like so. So the graph of our absolute value function is the red graph. It's a V that has a vertex at 2, 0, has a slope of -2 on the left side, +2 on the right side of the vertex. And now we can talk about integrating. If we're integrating from 0 to 5, that means we're going to have this region here in the first quadrant, 2, 3, 4, 5, this region here. Then it goes without saying that this graph is not drawn to scale. Let's find some values. In this first region, the triangle has a base of 2 and a height of 4. So the area of that triangle is half of the base times the height. The area of this region is 4. Over here, we have a triangle whose base is 3. Let's see what the height is. If x is 5, now let's put 5 in for x. 2 times 5 is 10. 4 minus 10 is -6. The absolute value Negative 6 is 6. So we have half of 3 times 6. The area of this region is 9. Since we're integrating from 0 to 5, we have a positive change in x. The y values are all positive, so our integrals are positive. Our integral is going to be 4 plus 9, which is 13. So now we can come back and just say that the integral of the absolute value of 4 minus 2x with respect to x, from x is 0 to x is 5, is 13. I'm going to suggest that whenever you get an absolute value function and you have to differentiate or integrate, just take a minute and sketch the graph. It'll help you at least come up with a plan of what we're going to do and how we will proceed. Well, hopefully this was helpful. Again, you can watch these videos and more on your own time outside of class. Hopefully I'm getting back from the meeting in time to answer a few questions. Well, good luck on your quiz. And after the quiz, your assignment is going to be to do the backside of this page, all the homework problems. Good luck, and we'll see you guys later.